Okay, so we're looking at regression lines and the change of variable, and also a hypothesis test for correlation. Now that's what was given in the advanced information. The change of variable, I suspect, could be an exponential change. So this is using your AS, like the last chapter in AS when you do exponentials. So that's what's in your specification. I've tried to write a question around it. Hopefully it works. Let's have a look. So we've got a school, starts a campaign, reducing student absences, not staff. And the idea is the absences go down. So we're expecting a negative correlation because as the weeks go up, we've got the lessons are going down. So the missed lessons are going down. Okay, so data is coded. We've got x equals t and y equals log s. So if you think about it, that graph that's being plotted is a graph of, on the x-axis you've got t and on the y-axis you've got log s. And you want to calculate the product moment correlation coefficient, and this is where this is important, between t and log s. Now you're not given log, you're given just s. So in your calculator you have to make sure you type in 1, 2, 3, 4, 5 into the x column and log 240, log 150, log 101. So for part A, if you're using the class whiz, you're going to menu 6, your number 2. In the x column, as I said, you're typing 1, 2, 3, 4, 5. In the y column, you're typing in log 240, log 150, log 101, log 65, log 45, and so on. And what you should get when you then you go out of it, you press option, you get a choice that says regression calc. And what you should see is an R value of minus 0.999. And you can just write calculation using calculator. Nobody is expecting you to do anything manual with that. It will probably only be worth a few marks. Part B, you're going to use your answer to explain why an exponential form is likely to be a good model. So first of all, we're going to say R is close to minus 1, showing strong negative correlation. So we're now saying because that R value, remember R values are between minus 1 and 1. Minus 1 is perfect negative, which this is very close to, and 1 is perfect positive, right? So showing strong negative correlation, points are close to a straight line. It's to straight line for t and log s, which can be rearranged to exponential form. Okay. You're then told that the head teacher believes that the campaign is showing promise. Okay, great. Carry out a hypothesis test to determine at 5% if there is evidence to support it. Now, hypothesis testing on regression is one of the easiest topics. So you're getting a regression line, you're getting a hypothesis test. You see that immediately, you're going to know that your H0 is this, well, it's a row, but it looks like a P. If you wrote it and yours looked like a P, not a problem. Row equals 1, and H1, you've got to think, what does that mean? Well, she is saying it's showing promise. So she's expecting it to have an effect. So to become, to stay negative. So less than 0. And now we're going to carry out the hypothesis test. So the first thing we need to do is find our critical value. So you're going to look at your formula book, and it's page 37 on your formula book, and you get this table. Now, the bit of the table we're interested in is our sample size, which it was 5 weeks. So we're going to go down to 5 and then 5%, which gives us this value here. So what we have found is that we are looking for this value here, which is 0.8054, and that is our critical value. So we're going to say critical value equals, and because we're dealing with a negative correlation, we're going to make it minus. We're always thinking about what's in the tails, okay? So we know that minus 0.999 is less than minus 0.8054 because it's therefore smaller in the tails. So it's weird. It's not what we expect it to be. We want everything to be in our happy space. If it's not there, we can reject H0. And we say there is evidence to suggest that the head teacher is correct. Right? So we're just talking about evidence. If it was the other way round, there is not enough evidence to reject H0 and show that the head teacher is correct. So we're always talking about evidence here. Okay. Then it goes on to say, show that the relationship may be expressed in the form y equals mx plus c, expressing m and c in terms of p and q. So if we go back to the beginning, we're given that the model can be given in this form. So s equals pq to the power of t. Okay. So let's take that. Oops. Right, let's put an extra sheet in. Yeah. Okay, so we can say s equals pq to the t. We're going to log both sides. Now, typically this means log to the base 10. You could do it to any base, but in stats, that's normally what we're using, unless it tells you otherwise. So then you've got log p. Remember, with logs, when you times them, you're actually adding them. And then also anything to the power can come down. So we get log s equals log p plus t log q. And now what you want to do is you want to compare it to y equals mx plus c. We know that y is log s. So we've got y equals log s. That's what we were given initially. We know that x is the same as t. Okay, so we're going to say x equals t. Now, in front of the t is the m. Attached to the t here, we have log q. So we're going to say our m is equal to log q. And we're going to say our c must therefore be log p. And that's your connection, and you're connecting which one is which. You're then told the regression line is found to be, so we're given this regression line, and we want to find p and q to two significant figures and also explain what they are in context. Okay, so looking at what we're given here, we can see that the gradient is minus 0.1817. So we've already said our m is equivalent to log q. So we're going to say log q equals minus 0.1817. Log p is equal to 2.5505. Now remember, we're assuming these to be base 10. So therefore q is 10 to the power of 0.1817. And p is 10 to the power of 2.5505. When you calculate those in your calculator, you get 0.66 and you get 355.2. So to two significant figures, that's going to be 350. All right, what does that mean in context? So if we look at part E, so this is part E, part 1, part 2. So it tells us, sorry, this should be 360. It tells us that when that value of P is essentially telling us what happens when this is 1. Now that's going to be 1 when T is 0, because anything to the power of 0 is 1. So when T is 0, that's when we're starting off. So there are 360 absences initially, or to begin with. And the 0.66 tells us the absences are reducing by a factor of 0.66 every week. And part F is a teacher work the whole academic year because you have to extrapolate. So what that means is you're taking data from, ages away. It doesn't make sense to do so. So extrapolation is not reliable. More than 5 weeks, not in data set. Not in data set. Something like that. That should be sufficient. Sorry, you can excuse the writing. So hopefully that makes sense for that question. And we'll have a look at the next one in a second. Okay, so here we've got measures of central tendency, which essentially means working out those averages, standard deviations, and so on. So generally we work out a mean and standard deviation together, and the mean represents your average, so your common point, and your standard deviation represents your variation. So how far something is away from the mean. Now, what you have to remember is the mean can move. You can add, you can subtract, you can multiply, you can divide. But how far everything is from the mean is only going to be affected, so the standard deviation and variance is only affected by multiplying and dividing, whereas the mean is affected by everything. This will make sense in a second. So let's have a look at this question. We're given some information, we're told it's been coded, and we want to find out an estimate for the mean and the standard deviation. Now, in your formula books, you're given your formulas, but you should know that at least the mean is going to be your sum of everything, which is what this represents, divided by the total amount, which is 200. So we're going to do minus 467 divided by 200 to give us minus 2 even, 0.335. And then our standard deviation, we're told, is the sum of Fy squared divided by n minus our mean squared. So 2.335, and it's negative, so if you square it, it's going to become positive. And that gives us our variance. To get our standard deviation, we've got to take the square root of that. And we're left with 6.36. Okay. However, this is an estimate for these coded variables, not for the actual mean, which makes sense because you wouldn't expect the lifetime to be negative. So the mean is easy. I said mean is affected by everything. In order to get to the y, what did they do? So they took a value minus 755, then divided by 2.5. So you're going to do the opposite. You're going to take your y bar, you're going to multiply it by 2.5, and then you're going to add 755. And we get 749 point something, one something, but 749 is a sensible way to put that. So we'll put it for 3 significant figures. For the standard deviation, however, it's only affected by multiplying or dividing by anything. So we don't do this minus bit here, or as we did add it back, we're actually just going to take the 2.5. So your standard deviation of x is going to be your 6.36 multiplied by your 2.5. You 15.9. Okay, so for part B, what would they recommend they use? Now, if you look at your interquartile range, it's significantly, well, it's higher than your standard deviation. So, and there isn't any evidence here that you've got extreme values. So that's when your interquartile range is, and your median is a bit more interesting, is if you've got extreme values, your mean will be affected by that, whereas your median won't. So what you'd say here is I would recommend using the standard deviation. And the reason that is it's standard deviation, and this is because it's lower, it's a lower value, showing less variation. And, you could also write no evidence of extreme values. Right, I hope that's useful. We'll look at the next question. Right, so let's look at probability and Venn diagrams. So as a general summary of probability, probabilities will always be between 0 and 1. So it's the chance something happens. In terms of symbols, we've got this symbol here, which is and. We've got or, so and is the bit in the middle, or is everything for those things. And you might have a dash, which means not. So over here, we're looking at explaining why A and C cannot be independent. So what kind of events do we know about? We know about events when A and B equals 0. These are called mutually exclusive. So these are two events that can never, ever, ever happen at the same time. It can't be Sunday and Tuesday in this room at the same time. So that's what we mean by mutually exclusive. However, independent, they can happen at the same time, but they don't depend on each other. So you deciding to wear yellow socks and me wearing a green jumper may happen on the same day, but they don't depend on each other. I don't call on you to check what you're wearing. The only way to prove independence is mathematically if we say that the A times B, the individual probability, equals the bit in the middle. So now if we have a look for part A, we're going to say, well, if A and C are independent, so if independent, then the probability of A times the probability of C would equal probability of A and C. We can see that A and C don't intersect, so equals 0. However, neither A, not having a great day for spelling today, neither probability A or the probability of C equals 0, therefore cannot be independent. Okay. For part B, we've got A or C and then not. So first of all, we identify our A or C. So everything in A and everything in C. And we want the not. So essentially we want the amount that we've not highlighted. So these two together. So we're going to have 3 tenths plus 1 quarter to give us 11/20. So it's the amount that's not in A or C. Okay. The next question says, given A and B are independent. So now we're told that they are independent and we want to find the value of P. Okay, so let's have a look. We've got the probability of A, which is 2/15 plus P. We've got the probability of B, which is 3 tenths plus 1 tenth, so 4 tenths plus P. And we've got the probability of A and B, which is B. Now we know if they're independent, if we multiply these two together, we're going to get this. So let's do that. So we get 2/15 plus P multiplied by 4/10 plus P equals P. Right. Now you could have multiplied something out, but it's easy just to use our log multiplication. Opening our brackets. So 2/15 times 4 tenths. So we're going to get 4/75 plus 2/15p plus 4/10p plus p squared equals p. Now we're going to put everything onto one side, and that's going to give us p squared minus 7/15p plus 4/75 equals 0. If you want to make that easier or nicer to look at, you could multiply everything by 75. So you'll get 75p squared minus 35p. For those of you that looked at the previous set of solutions, the answers I believe are correct, but I think I accidentally wrote that plus 35 as a and then minus 35 is a plus 35. So when I was writing them up. And we end up with P being, you stick it into your calculator, 4 over 15 or 1 over 15. Right, so to figure out which one of those it is, we know that the whole thing has to add up to 1. So we add everything up. And when we do that, we get 2/15 plus P plus 3/10 plus 1/10 plus 1/4 plus Q equals 1. And that rearranges to tell us P plus Q equals 13 over 60. Now, if we were to substitute in P equals 4 over 15, what happens is you're going to get 13 over 60 minus 4 over 15, and that's going to give you a negative value for Q, which is impossible. So you can put them in anyway. So Q is 1 over 20 or 1 over 60. If we use 1/5, I think I've written 1/15 here. Let's change that. Okay. And so we'll say this one is not valid. And so therefore our answers are P equals 1 over 5 and Q equals 1 over 60. So if we make sure that's correct, we can sub them back in and we can double check we've done that right, which we have, and that's your final answer for those two. So I'm going to replace that with 1 over 5 and that with 1 over 60. And now it says find the exact value of A given B or C not. Okay, so remember what we're going to start with always is the thing after the given sign. So I want to highlight everything that's not in B or C. So I want this bit and this bit. Those are the two things that are not in B at all or not in C. So what given means is essentially you have made your world smaller. All you care about and all that this is going to be out of is those two values. So out of those two values, what you're trying to say is how much is A? Well, we can see that's 2/15. So then when we plug that into our calculator, our final answer comes out as 8 over 23. Okay, so I hope that makes sense as well. Given essentially means you're making your world smaller. Okay, we've got a question about a discrete probability distribution with a normal approximation. Now, the only discrete, well, you can have discrete where you have a probability distribution where you have a table, or you've got binomial distribution. Now, as we read this, we don't have a table. There's not a table to put together. So we know this is going to be a binomial question. So anyway, when Sam collects a counter, she's picking red or blue. We've got a probability and we've got a set number of trials. So straight away, we know it's binomial 11 0.4. And part A, we want the probability x equals 2. And for part 2, we want at least. So at least means greater than or equal to. Now this is going to go into your calculator. If you've got the class whiz, CD only gives you less than. So this is 1 minus less than or equal to 4. You want to keep the 5, so you're getting rid of the 4. So you substitute that into your calculators and you get 0.4672. Right, and then we now have, it's got bigger. So now we've got 300 counters and we're going to use a normal approximation. So for part B, we know when we normally approximate, the mean or mu is NP and the variance is NP, oh, no, that's quite weird, NP multiplied by 1 minus P. So here we're going to have 300 times 0.4 and that gives us 120. and that's our mean, and then our standard deviation, or squared, which is our variance, is going to give us 72. Okay, and we want to find out she's going to receive at least 135. So remember, at least, all right, so let's put that there. So we want to estimate the probability our new y is at least, so greater than or equal to 135. Now we have to do what's called continuity correct. And essentially, all you do there is make your range bigger. So if I've got 135 and I'm doing everything bigger, I've got to make, everything larger than. I want to make my range bigger than 0.5. So actually, I've got to start at 134.5. I put that in along with my normal distribution numbers. So we had y is normally distributed 120 and 72. So you stick that into your calculators and you should get 0.0437. So that's your binomial distribution with a normal approximation. Okay, we've got a normal distribution question here. We're told that Sarah, tuning her radio station, is normally distributed 433 and a standard deviation of 4, which we square. So she wants a radio station with 440. We want to know the probability that RS is less than her 440. You're going to use your calculators. Remember, equals doesn't mean anything in normal distribution because it's continuous. So the slither is so small, if you ever get asked anything with equals, it's just 0. So we're trying to find the probability S is less than 440. And we get 0.9599. And then we're going to look at more than 5 kilohertz away. So if we think about that, that means it's got to be more than between 435 and 445. Oh, not sure what's happened there. Yeah, 445. Okay. So, but we want everything else. So what we can do is we can find the probability from 435 to 445 and do 1 minus it. And when we do that, we get 0.6928. Okay, so now she thinks it's going to be less than 433. And when she works it out, she gets a mean frequency. This should say 432. So what we're going to do is do the easy bit first. So H0, mu equals 433. H1, mu is less than. Now this is always the same. It's hypothesis, your H0 and H1 you should always get right. And because we've got a sample, we had a sample, I believe, of 20, yes. Then you've got to use this X bar where you write your mean. And then you have your standard deviation squared over your n. So we want the probability this X bar is less than 432. Gives you 0.0368. So 0.0368 is less than 5%. So you've got to reject H0. And you say there is evidence to suggest Zahra is correct. Is correct. And you probably should start by saying reject H0. Right, last bit of this section. We've got Jake is tuning in to listen to his music. And we've got a normal distribution. This is going to be our mean. We've got a value of 438 here where everything less than is 0.2. We've got 445 where everything bigger than is 0.1. And what we're trying to do is work out our mean and standard deviation. So what we need to recognize is this is something to do with our Z, which is our standard normal distribution, and our connection between Z and X is X minus mu over sigma. Now the thing to remember, Z is just another axis where we've coded this mean and made it 0. And we're going to use the same logic on the two that underneath. So if we say 445 minus mu over sigma and 438 minus mu over sigma. Now, you don't know what those mean necessarily, but we need to then find out the inverse area to be able to equate it to something. So in your calculator, you could do inverse area, and it will, for Z, I mean, it gives it to you on the tables, but if you use inverse calculator on your inverse area on your calculator, you should be able to get there quite quickly. And then we end up with two nice simultaneous equations to solve. So that one equals 1.2816. I'll let you solve those, but you end up with a standard deviation of 3.3, and they want it to one decimal place. So your mean is going to be 440.8. Okay, let's look at hypothesis test. We have some weight of some jelly beans, which is normally distributed with some mean and some standard deviation. We've been given the probability of W minus mu is greater than 20, but because we don't have values, we're going to use our Z world, if you remember, which is normally distributed 0, 1, and Z is X minus mu over sigma. Now what we want to do is find the probability of W minus mu less than 20 equals 0.001. So we're going to change it into Z's. We've already got W minus mu, and we know that is greater than 20, but we're going to use 20. And then we've got over the standard deviation, the inverse and the area of 0.001 is 3.902, which gives you 6.47, which is what we're looking for. Now for part B, we've got a sample with normal distribution. So remember, we need to do that X bar, where the n remains the same. So our n in this case is, well, we've not calculated it, but it tells us in the question that the mean weight of 500. Our standard deviation is what we calculated as 6.47 squared over our sample, which is 10. And what we're trying to do is we're testing a hypothesis again. So H0, always the mean. H1, we're saying it's less than 500. And we're going to calculate it X bar, follow the sign that's in the H1, which is less than. And that's, we're going to say less than, and we've got 4950 divided by 10, which is going to give you 495. Stick that in your calculator, 0.0073, compare it to 5%. It's less than 5%, so we can reject H0, and there is enough evidence to show mean weight less than 500 grams. Okay, so I hope that makes sense. That's the last one from the stats paper. There's quite a lot in the mechanics because it's not as defined. Hopefully those will all be with you soon.